Right now, all across the Milky Way, new stars and planets are being formed out of swirling disk of dust and gas. And thanks to surveys such as ALMA or the VLT, we can study the outer parts of these disks and observe the formation directly. But what about the innermost regions of the disk that are just too fine to be resolved? I'm John Bredall, a recent graduate from the University of Hawaii at Manoa, and in this Aloha brief, I'll be discussing how we can probe some of these inner disk regions by studying a certain kind of young star known as a dipper. Stars form when clouds of gas collapse from their own gravity. Conservation of angular momentum flattens the particles out into a spinning disk, and in the center, a young stellar object, or YSO, slowly begins to form by accreting material from the inner disk. Further out in the disk, planets begin to take their shape, as shown by the recent VLT image of AB Aurigae. The combination of all these physical processes means the light that we observe from a given system will vary, such as getting brighter from increased accretion rates or getting dimmer from material passing in front of the star. If we classify these young stars based on the variability we observe, we will have a useful reference for which systems to look at when wanting to study a given phenomenon. This paper focuses on dipper stars, which exhibit quasi-periodic dimming events believed to be caused by dust from the inner disk region obscuring the central star. We start by using the All-Sky Automated Survey for Supernovae, or ASSASSIN, which consists of 20 telescopes at 5 separate locations across the globe. This wide latitudinal and longitudinal coverage means that the entire night sky can be scanned roughly once a night, providing us with 4 to 6 years of data for any given star brighter than the 18th magnitude. With a list of pre-selected YSO candidates, we generate ASSASSIN light curves for different sources in Lupus. We then classify these stars based on 2 criteria. First, by how periodic the dominant variability signal is, and second, whether this variability is predominantly brightening, dimming, or symmetric. In doing so, we find 11 stars in the Lupus region to exhibit variability consistent with the dipper type. By examining their infrared excesses as measured by Ys and 2 mass, we confirm there to be an indication of full disks around the stars. Smaller dust grains are more effective at blocking blue light compared to red light, and the more dust that obscures the star, the redder it gets. This is why sunsets and smoke from forest fires make the sun appear red. Conversely, larger dust grains begin to block out longer wavelengths. By combining observations from ASSASSIN and TEST, we can compare dip depth with the amount of reddening and derive a linear relationship, the slope of which is an indicator of the grain size distribution of the dust in the inner disk region. 5 of our 11 dippers were observed by TESS, allowing us to measure the reddening of the dust for each system using this method. However, 3 of these sources lie in crowded fields, and our reddening estimates may not be fully reliable for these systems. For more information, see the paper on the archive. We also obtained multiband observations of 5 of the dippers using the Las Cumbres Observatory telescope network, allowing us to perform a similar calculation of reddening that isn't as affected by crowded fields as the TESS observations. Overall, we calculate the reddening values, and by extension the grain size distributions, of 9 of our dipper systems, one of which, RY Loop, had data from all 3 telescopes and showed consistent values from both methods. By comparing the values for dust reddening with infrared excess, we find a potential relation between the size of the dust grains and the apparent temperature of the inner disk. More observations from larger and more in-depth studies are needed to confirm this relation, however. This work highlights the synergy between ground and space-based observations and how they can better our understanding of circumstellar disks and the planetary formation processes. By studying dipper stars, we can probe regions of these disks that are otherwise difficult to resolve with current interferometers. For more information, see the link to my paper down in the description below. To see more Aloha briefs, please subscribe to the IFA YouTube channel. Mahalo.